So following on from Chris Onions and Lowell Collins' research into the loads generated by rafts on a high line, it made sense to complete the set and look at sleds on a high line and a rescuer on a quick release harness on a high line as well. Now, Chris had attempted to get some data on sleds, but due to the lack of sensitivity of the load cells he was using, the results were inconclusive. We now have access to more sensitive load cells and have now successfully collected some data for sleds and harnesses on a high line. Now, while the data for sleds is not yet ready for release, the data for quick release harnesses has provided what are hopefully some interesting findings. Due to the large amount of water time for the in-water rescuer, we chose to use a Rescue Randy mannequin rather than subject a rescue technician to 3 days of suffering. This gave us the advantage of a uniform body shape, but the disadvantage of sacrificing a small amount of real-world effect. On balance, it was felt that the mannequin provided an acceptable solution. A high line was rigged and a load cell placed on the raised lower line. Once the mannequin had been positioned, it was allowed to settle for at least a minute. 10 flow velocity readings were taken 50 centimetres in front of the mannequin, allowing a mean flow velocity to be calculated. A minimum of 1.5 minutes of force data were then collected at a sample rate of 500 samples a second. The mannequin was then moved to a new location and the procedure repeated. A total of 51 data sets were obtained over a 3-day period. Now, if the drag force of the in-water rescuer is calculated, in this case our mannequin, using the 51 data sets and the following formula, then a graph showing an exponential curve is the result. Here, the vertical axis shows force on the rescuer in kilonewtons and the horizontal axis shows water speed in meters per second. This is a very similar graph to the one that would be produced if you were to use the square law referred to in the WRT and water and flood rescue manuals. If, however, the complete data sets are plotted onto the same graph, then we get quite a different picture of what is actually happening. If this graph is examined, then obviously the real-world data in orange does not follow the drag force exponential curve in blue. Instead, we get a linear progression at a much shallower angle. This obviously indicates that something is happening. It seems fair to deduce that as the velocity of the water increases, there is a change in shape of the rescuer in the water. We have all, I am sure, had that rising up feeling when held in the flow on a harness. So in the same way that a skydiver in the standard spread eagle free fall position will typically reach a speed of 120 miles per hour, by altering their position to a head down dive position, they reduce their surface area in relation to drag force and so can reach speeds of up to 200 miles per hour. This is what is happening with the rescuer in the water. As the velocity of the water increases, their body position changes in relation to the current vector. And so we see a linear force progression. It is clearly not an obvious coming up onto the plane with a subsequent drop in the force on the system that we see with a raft, but there is some planing going on. This, I think, begs 2 questions. Firstly, what is the maximum tolerable force that a rescuer in the water can sustain, and therefore what is the water speed at which this is experienced? And secondly, what is the maximum water speed at which an in-water rescuer can realistically operate? Now, data from traffic collision testing does not really help us here, as this concentrates on a peak impact force. The area that is useful to us is research that looks into the behaviour of crowds and the associated crush injuries that sometimes accompany these events. Here we find that from real-world testing, the tolerable force for men pressed against a 100mm wide flat bar is 0.623 kilonewtons. From our testing, this would equate to a water velocity of around 3.3 meters per second. Now, these figures need to be treated with a degree of caution, as the force for women was reported as being significantly lower, and loadings were affected by various factors including age, gender and anatomical build. Secondly, perhaps of more relevance, is the current velocity at which an in-water rescuer can reasonably be expected to operate. So from discussions with experienced rescue technicians and Rescue 3 trainers, it seems that the higher flow velocities recorded in the test were toward the upper end of the scale in terms of an in-water rescuer being effective. So we can suggest that a flow velocity of around 2.5 meters per second is the realistic maximum for effective operation of quick release harness on a highline. At these speeds, the in-water rescuer was experiencing a force of somewhere close to 0.5 kilonewtons. Just as in the previous point, this figure needs to be treated with a degree of caution, as what is tolerable and effective area of operation will be affected by various factors, including age, gender, anatomical build and experience. So what does a flow velocity of 2.5 meters per second actually look like? Here we have a rescuer positioned on a highline in a laminar flow of that speed. As can clearly be seen in the footage, they are still able to function effectively, not being overwhelmed by the force of the water, able to give directions if required, and capable of effective and secure casualty handling. All this being said, the rescuer in this instance had had enough of the pressure after nearly 5 minutes on the line and was more than happy to release. So what are the questions raised? Does the position and the point of attachment on the quick release harness have an impact on the amount of force in the system? Now, many North American manufactured PFDs place the attachment point lower on the PFD than many European manufacturers. This will surely change the orientation of the in-water rescuer and may have an impact on the amount of force experienced. The study demonstrated that there is a change in shape of the in-water rescuer as flow velocity increases. So is it possible for the in-water rescuer to adopt a shape that reduces the force being experienced? If this is possible, is it realistic to be able to operate effectively while maintaining this shape? And the final question not addressed by the study is that of, once the victim has been collected, how does this increase the load experienced by the in-water rescuer? And on any retrieval back upstream, how does this also increase the load on the rescuer?